extended Euclid's algorithm. In Z10, the two numbers A and B are multiplicating inverse to each other. A and B are multiplicating inverse to each other if A into B is congruent to 1 mod n. In their case, A is said to be B inverse or B is said to be A inverse both in mod n. Not each integer has a multiplicative inverse. Only if GCD of A comma n is equal to 1 only multiplicative inverse exists. That means if both A and n are co-prime then only inverse exists. So extended Euclid's algorithm can be given in the statement of S into A plus T into B equal to GCD of A comma B. So here it is used to have multiple purposes. One is it is used to find GCD of A comma B. Another one, it is used to find A as the inverse of B or B as the inverse of A. So these are the two purposes of extended Euclid's algorithm. Now let us assume we are going to take two numbers 73 and 20, and now what I want to find is I want to find 20 inverse mod 73. Under mod 73, what are the inverse of 20? That is what I want to find. So let us use the extended Euclid's algorithm. For the extended Euclid's algorithm, you need to initialize some values called T1, T2, T3. T1 must be initialized with 0, T1 must be initialized with 1. So this is the initial values. And how to obtain T3? T3 can be given as T1 minus Q into T2. So this is what we are going to obtain. So let us form one tabular column by keeping these initial values. I'm going to write that. What are the columns? Element means the number. Let us take that R1, R2, or let us take the same way what we have taken here. Here we have taken as A into B equal to GCD of A comma B, right? So let's take the same thing. A and B, and let us take Q and R. In addition to that, the new values T1, T2, T3. So this is what I'm going to add. I'm going to add like this. So when you look into this, you can clearly understand that I've created a table with number values like this A, B. So here what I need to do is, what I want to find, I want to find 20 inverse mod 73. Okay, so now place the number larger number 73 here and number 20 here. And for these two numbers, Q and R, Q is the quotient, R is the remainder. And what are the initial value you have? T1 is initialized to 0 and T2 is initialized to 1. So let us think these are the initial steps of the algorithm. Now what I want to do is, I'm going to perform the calculation. What is the first step? A divided by B. Divide A divided by B. 73 divided by 20. So I'll have 3. 320 is 60. So I'll have 3. 320 is 60. What is the remainder? 73 minus 60 is 13. The meaning is when I perform division by 73 by 20, quotient is 3 and remainder is 13. And now compute T3. What is T3? T1 minus Q into T2. What is T1? T1 is 0 minus what is Q? Q is 3 into what is T2? 1. So 3 into 1, 3. 0 minus 3, minus 3. So I am making is minus 3 in T3. Now what are the next step I am going to do is I am going to shift the values. What I am going to shift? Ignore X. Here ignore X. Shift B to A. Shift R to B. Similarly, ignore T1. Shift T2 to T1 and shift T3 to T2. This step will be iterate for every step. Now let us repeat one more time. Now, now old value of B will become new value of A. Here comes 20 and R becomes B. So 13 comes here. Likewise, T2 comes here 1 and T3 comes here minus 3. Now I am going to perform this step, this iteration 20 divided by 13. Quotient is 1, remainder is 7. Right? Then I am having is T3. What is T3? Q1, T1. T1 is 1 minus Q into T2. Q is here we are having Q is 1. You have to look the current table 1. Current iteration 1. So 1 into what is the value of T2? Minus 3. So into minus 3. So 1 minus of minus 3, that will become 1 plus 3 will become 4. So T3 becomes 4 here. Now the next step, what I need to do? Again, shift 13 here, 7 here, minus 3 here, 4 here. Now my table will look like this. 13, 7, minus 3, 4. Now again perform 13 divided by 7 is quotient is 1, remainder is 6. Here I am having T3 is T1 minus Q into T2. T1 is minus 3. So minus 3 minus Q, what is the value of Q is 1. 1 into T2 is 4. So minus 3 minus 4, which will give minus 7. So T3 becomes minus 7. Now progress to the next step. Shifting 7 comes here, 6 comes here, 4 minus 7. Now make 7 divided by 6 is 1. Quotient remainder is 1. Again you repeat this step. What is the value of T3? T1 minus Q into T2. So 4 minus Q is 1. 1 into 7. 1, we'll have this as, we'll have 11 minus of, here minus 7, here minus 7 into 1, minus 7. So 4 minus of minus 7, 4 plus 7, we'll have 11. So now T3 becomes 11. Again make a shift, 6, 1, minus 7, and then 11. Now perform this. 6 divided by 1 is 6 quotient and remainder is R. R is 0. So perfect division here is 0. Here I'll have, what will have? For T3, T1 minus Q into T2. T1 is minus 7. Q is 6 into T2 is 11. So minus 7, sorry, minus 7 minus. Minus 7 minus 16 plus 11 is 66. So minus 7 minus 66 will give me minus 73. So here my value becomes minus 73. Now, when I need to stop this, I cannot continue this because the remainder becomes 0. Or we even write the next step, here 1, here 0, here 11, here minus 73. Now at this tenure, when you have denominator is 0, we cannot further continue. At that time, whatever is in the number T1 will be the inverse. So here I am having 11. So the final value is 11. So from this table, it's whatever the table I entered when B equal to 0. When I am not able to perform division further, I'll stop the algorithm. At that time, what is the value of T1 will give me the inverse answer. Now, from this, we have obtained that 20 inverse mod 73 is equal to 11. This is what we got. Now, let us check it out this, if it is a multiplicative inverse or not. Check it out in this way. 11 into 20 is 220. Now, make 220 mod 73. What will you get? 73 into 3 is 3 3s are 9. 3 7s are 21. So 373s are 219. So the remainder is 1. So we got that 11 into 20 is congruent to 1 mod 73. So what is the meaning of this? Under modulus 73, 11 or 20 are inverse to each other. So in this way, extended Euclidean is used to obtain the multiplicative inverse of any number.